Welcome to Lesson 15. So we talked about scatter plots and correlation as well as the least squares regression line. Now we're going to talk about a specific part of that regression line, the slope. So we're going to talk about by how much the response variable changes, either increases or decreases when we increase the explanatory variable. So estimating parameters. So in theory, if we had all observations in the entire population, so let's say if we were still using that GPA example, we could have all folks that had their first year college GPA and their graduating high school GPA, and we could make a line. And the line that best fits everybody in the population, that's a population line. So that line would have the equation mu of y, so the mean of all the y values is equal to beta 0 plus beta 1 times x. So when we see betas, those are Greek letters. So beta 0, beta 1, Greek letters. B0 and B1, not Greek letters. That means that we're estimating them from a sample. So in general, if we want to try and estimate whatever that population line would be, which is usually what we're after, we're going to estimate it. So we're going to have y hat. So a hat usually signals right off the bat, hey, this came from sample information. We are estimating using sample information, is equal to B0 plus B1 times x. So B0 is an estimate for beta 0. B1 is an estimate for beta 1. So that slope of that population line and that y-intercept of that population line. So parameters versus statistics. So in this scenario where we're talking about linear regression, so we have those lines, this y-intercept is going to have that notation beta 0. So if the true population, so it's going to be the mean of all the y values in the population when x, or the explanatory variable, is equal to 0. And so when we estimate it, we're going to use the notation B0. Note, if you look at some other books or you look online, you might see beta hat 0. The hat implies that it's an estimate from the sample, so be careful. Similarly, if we're looking at the slope, which is beta 1 of the population, we're going to estimate it using the slope from our sample line. You might see a beta 1 hat that if you go around online, we're going to use the notation B1. So things to know, we usually don't try to make statements about the population y-intercept. And we might go ahead and say, hey, you know what, given our least squares regression line, we predict this. But we're usually not going to ever run hypothesis tests or confidence intervals on beta 0. We don't usually care to test it that badly. It's not our focus. Usually our focus is going to be that value of the slope. We want to know what's happening to the response variable when we change the explanatory variable. We want to know, hey, if I increase the explanatory variable, is it increasing or decreasing the response, and by how much? We're really interested in the slope. Similarly, the mean of all the y values for a specific x value, we're going to estimate with y hat. Sigma, this tells me how much variation we have around that line, because most of the time we're not lucky enough to have all of the points fit exactly on that line. And we estimate it with S, which is the standard deviation from that sample. And so we want this to be small. We want the variability for our predictions to be small. We want it to be pretty close to that line. We want the values or the points observed to actually be really close to the line. So estimating parameters, what is sigma? So we kind of just briefly introduced it on that last slide there. So we want to estimate, so what if we estimate that population line, we want to figure out how much those points, the actual observations vary around that population line. So we can estimate it by using the regression standard deviation S. So here's an equation. This is not typically something we will have you calculate by hand. It is a little tedious, but there is the equation, just so it's not this magic number out of nowhere. So if we are to square this value, so basically get rid of the square root sign, S squared is also referred to as the mean squared error. So if we gave you the mean squared error, you could take the square root of that and you would have S, essentially. Or if you had S and you squared it, then you would have the mean squared error. It is often used to describe how well the model fits. Well, there's got to be a little more context than it by itself, but we're not going to go too far into it. We're not going to say, hey, here's the mean square error, tell us about how it fits. Not too much, not right now. So hypothesis test. So if I want to run a hypothesis test for the slope, note we're not going to usually bother pretty much ever running a hypothesis test on the y-intercept. It's a little weird. We're usually just going to leave that in there every time. So the setup, the null, we're going to start off by assuming nothing interesting is happening. The null is always nothing interesting is happening. So we're going to say there's no relationship between x and y. X is not a useful predictor for y. X is not a significant predictor of y. Notation-wise, it's going to look like this. It's going to say, okay, beta 1, so that's specifically the slope, is equal to 0. The alternative is saying, oh, no, wait, there is a relationship between x and y. X is a useful or a significant predictor for y. Obviously, replace x and y with the actual variable names. And the alternative is going to be beta 1 is not equal to 0. So things to note, it's always going to be a not equal sign. It's always going to be a two-sided test. For this scenario, it will always be two-sided. So calculating a test statistic here. So given that we went ahead, you put together your scatter plot, fit the least squares regression line, and then you looked at your residuals and decided, okay, I meet the 4 conditions. I have linearity, independence, normality, and constant standard deviation. You can go ahead and know that, so this is my t-stat, or my t-test statistic. It has your sample size minus 2 degrees of freedom, so it's a little bit different than when we were using t-methods before. And we can perform a t-test just on the slope here. So it's going to be equal to b1, so the estimated slope from your output, minus, like, claimed. So from your null. So your null, if you remember, it was saying beta 1 is equal to 0. Just plug in 0 here. It pretty much, that goes away. Over the standard error for B1. So that's a little trickier. It's this equation here. Once again, this is not something we will force you to calculate by hand. If you have software or software output or a calculator, this is something that you would get from that. So it's just going to be B1, so your estimate for the slope, over your standard error for the slope. And we will review like where that is in an output table as well. So then if you want to find a p-value from there, you take that test statistic and you find, if you use a t-table, you use the t-table, find your one-sided p-value, multiply by 2, And that two-sided p-value is your p-value for that test statistic. But remember to use the n-2 degree freedom row. So we're going to do this for the GPA example. We really, really are just big fans of this example for some reason. So the least squares regression line for high school GPA versus college GPA, this is just from those previous lessons. So I'm going to even throw in a hat. I feel better having a hat. So predicted freshman or first year college GPA is equal to 0.69 plus 0.78 times your high school GPA. So you can write X, but if you write X, you should write X is equal to high school GPA somewhere. So now we want to test whether the relationship between high school GPA versus college GPA is significant. Basically, is high school GPA useful in predicting college GPA? That's what we're getting at. Is it useful? Is it any more useful than just guessing the average college GPA, really? So our hypotheses, we're going to start off saying our null is saying, hey, high school GPA is not useful in predicting college GPA. And then the alternative says, yes, it is. High school GPA is a useful predictor for college GPA. So just to visualize what we even mean by that, I don't know about you, I'm a very visual person, so it's helpful for me. If the null is true and high school GPA is not useful whatsoever, we still have our scatter plot, but we could just fit a flat line and that would be just as good as any other line. That's what that's saying. So this flat line, technically, it's actually y bar. So if I just took the average college GPA, knowing high school GPA tells me nothing. I'm just going to guess the average college GPA and it's going to be good enough. However, if the alternative is true and the slope is not 0, so it's saying a flat line is not good to use, that means that pretty much a non-flat line will be best. And not only best, but it'll be, it's going to be better. It's going to be better by enough to really matter here. So if the null is true, a flat line is good enough. If the alternative is true, no, it's not. We don't want a flat line. We could have a line that fits a lot better and is a lot more useful. So here is the output. You could get this from a calculator. The data set itself is, I want to say we throw it in towards the end of the last lesson. So if you wanted to throw this into a calculator yourself, you're welcome to. So just a reminder, the sample size was 10. There were 10 students in that data set. So looking here, this is intercept. So this is all stuff that goes with like 0, so B1. So here's my estimate here, that 0.7758. There's probably a little rounding. I'm sure it goes past 4 places. My standard error is just going to be 0.1937. Beta 1, so what's claimed? So from the null, remember we just said it was equal to 0. Not super exciting. In fact, I love subtracting 0. It just goes away. And then degrees of freedom, remember that's n-2 here. So now it's a little bit different. The reason it's n-2, I have a B0 and a B1. So it's n-1 for each of those. So it's going to be 10 minus 2 is 8. So now I have everything I need to plug in. Conveniently, I also have a table that I can check my answer. But if that was left blank, which, hint, we love giving y'all tables that have blanks in them and then making y'all solve. It's our bread and butter. I don't know why. We're obsessed with it. So just know that's something we might do. So 7758 minus 0 over 0.1937. And it should be somewhere around that 4.006. Definitely double check. With the rounding there, it might be a little bit different. Not a lot different though. If it's a lot different, something went sideways. So now we have a t-test statistic. We have our degrees of freedom is equal to 8. We can use a t-table or software to find a p-value. So our t-test statistic is at 4.006. Our degrees of freedom was equal to 8. And remember, we are doing a two-sided test. The alternative for this test is always two-sided. So this tells me which row to use. So 8. And so now I'm going to try to find where 4.006 is. So like, it's not between these two numbers. But these numbers are getting bigger. I would argue that 4.006 is between 3.833 and 4.501. I'm not sure exactly where in there it is, but it's somewhere in between those two numbers. So I go up. So my one-sided p-value, it's going to be between those two numbers. Remember to put the smaller one on the left. So 0.001, 0.0025. It is super easy to goof up the order because if you use the order that they have here, it's going to be backwards. So I want a 2. So we want two-sided. So we want a two-sided p-value. That means we have to multiply everything by 2. So by 2 times 2 times 2. So my two-sided p-value is going to be greater than 0.002. And less than 0.005. And we would be perfectly happy with that. That would be fine. If you plug this into a calculator and got a more exact value, that would be fine as well. Just a throwback to that last slide, that p-value, 0.0039. 0.0039 is between 0.002 and 0.005. So we're good. If it wasn't between those, something went sideways somewhere. They should agree. And we're perfectly happy if you say, hey, with a p-value of 0.0039 or with a p-value between 0.002 and 0.005. We're happy with either. So conclusion, we want to know, and none of these are going to be complete on their own. We just want to know, hey, which of these statements are true? So I'll give you all a minute and I'll read through them. Okay, so for option A, it says we reject the null hypothesis that the coefficient for high school GPA is 0, given a significance level of 0.01. So if the significance level is 0.01, we have a p-value that's smaller than it, so we would reject. So we would reject, that would be correct. And it is the coefficient or the slope coefficient for high school GPA. It's worded a little awkwardly, but this seems true. So moving on to the next one, because as you can see, one of these is all of the above, so it is possible all of them are true. So given the p-value of 0.004, So it looks like they rounded the 0.0039 up. There is convincing. It's also okay to say very strong. We're totally okay with either. Evidence that there is a relationship between high school GPA and first year college GPA. So given our p-value, we have very strong evidence there is a relationship that high school GPA helps predict first year college GPA. And then I would argue, yes, this is true as well. So that's promising. I mean, hopefully C comes out to be true as well. Otherwise, we'll have to reinvestigate. So given our p-value of 0.004, there's convincing evidence that high school GPA is a good predictor for first year college GPA. Yes, so they have a relationship. High school GPA is the predictor. It's what happens chronologically first. Yes, we have a good predictor. Note, this does not mean high school GPA causes the college GPA. We don't know that, and we can't really know that without doing some sort of weird experiment, but you can't randomly assign people their high school GPA. So this is strictly observational. There are a lot of factors that go into folks' GPA besides just their high school GPA. So we can't say one causes the other, but we can say this one helps me predict the other. So I would argue all of the above here. Definitely, we can still write it up as a two-part conclusion. We would be saying, oh, okay, well, we reject the null hypothesis with a p-value of 0.004 at the 0.01 significance level. There is very strong evidence that high school GPA is a good predictor for college GPA. I might throw in whatever the population is. I think it was for this particular private college. They didn't give us that information in this scenario here, though. So then this is a little bit trickier. Confidence interval for the slope. So the confidence interval, it has a familiar form. So our point estimate plus or minus some critical value. So critical value means either Z star or T star. It's going to be a T star in this scenario, times the standard deviation or standard error of the estimate. So in this particular case, if we want to do a confidence interval for the slope coefficient, beta 1, we would use B1. So B1 is our point estimate. So if I want to estimate the slope for that population line, my best place to start is going to be the slope for my sample line. Plus or minus, so T star, so remember our degrees of freedom are n-2, times the standard error for B1. And we'll get that from a table. So yeah, that T star critical value, it's going to be a T star, so you can get that from the T table. Use the degrees of freedom n-2. And then it's going to be the same formula to calculate the standard error for B1. But typically, it's going to be a scenario where you have access to a calculator or software, or if it's like an exam, we're going to give you a table that has like the output. So looking at my GPA example, so we are looking for, we want to have a, what level confidence are we doing? We're going to do 99% confidence because we used a significance level of 0.01. That's why. If it didn't say and we didn't have a significance level, we would have gone with 95. So things to keep in mind, my sample size is still 10, my degrees of freedom are still 8. I'm focusing right here. So my point estimate, 7758, my standard error, 1932. 0.37. There we are. We have everything but T star. We have to figure out T star. So I'm going to go back to this table. So if I want T star for 99% confidence interval that has 8 degrees of freedom, I need to use the 8 degrees of freedom row. And then if I look at the bottom, I'm going to line it up with 99% confidence. So 3.355. That'll be my T star. 3.355. So it is going to be important to have this detail. If there is a scenario like this and you plug it into your calculator program and it calculates the interval for you, that's great, but we are going to want to know what T star is. That's absolutely going to be a component of if we ask for a setup. So looking here, my point estimate is going to be that 0.7758 plus or minus. I like to put this all in parentheses. It reminds me to do the multiplication first. 3.355 times my standard error is that 0.1937. So if I were to multiply first, this is not mental math for me, so I have to pull up a calculator. This ends up being something like 0.6499 if I round to 4 places past the decimal. So plus I like to add first and then do the subtraction. You are welcome to do it whichever way. Positive 1, 2, 5, 9. So yeah, and know that it would have been okay. Like you would not have had to cut it off if it went to 0 or if it went to negative values. It just gets a little bit trickier to do the write-up. So we estimate that slope coefficient, it goes from 0.13-ish to 1.4. So we basically estimate that for every 1.0 increase in high school GPA, we predict that the college GPA with 99% confidence will increase from and I say increase because these are both positive, from 0.12 to 1.43. So with a point estimate of 0.78 increase in college GPA. Okay, so for interpreting the slope, we are going to say for a 1 unit increase in X, we think this is what's going to go with Y. And we can combine this with the 2-part write-up for a confidence interval. So for this GPA case, we can interpret the slope as an interval estimate. So with 99% confidence, the slope estimated for each 1 point increase, so 1.0 increase in high school GPA observed, we estimate that the average first year college GPA will increase 0.13 points to 1.43 points, with a point estimate of a 0.78 college GPA increase. So it's not necessarily saying that it causes this increase, but it's associated with an increase here. So when we see the high school GPA get higher, we also see the college GPA get higher, which isn't too surprising. We'd be a little surprised if it got lower. If we had negative values in our confidence interval, that would have been associated with a decrease. So that's worth noting. And since we did not have 0 in our confidence interval, which agrees with our hypothesis test, if we had if we had negative numbers to positive numbers, we would have estimated a decrease of whatever to an increase of whatever. It's kind of confusing to write. Just know that negative numbers are decrease, positive numbers are increase. So reading statistical software output. So in general, this right here, you can forget that. We are never going to focus on that. I have seen once where in my master's program they had us doing that. It was kind of weird. Trust me, it is weird to not have a y-intercept. If we are focusing on doing hypothesis tests or confidence intervals for the slope, it's just pretty much going to be this row here. So whatever your explanatory variable name is, I think in that other table was HS for high school GPA. And then ideally, I mean, not always, but the table will have whatever your estimated standard deviation is there. So these two are relevant if you want to put together the least squares regression line equation, but it's going to be this row right here that you use if you want to do the hypothesis test or confidence interval. So reading, this is software output for the GPA example. If you look, they grabbed this, the row that says estimate is saying, okay, well, this is, your B's. So this is B0, B1. They just plug it in right here. And then further, they have an estimate for S. So estimated sigma, that's S. Your standard error for B1, it's going to be the standard error, the row that goes with B1. Your t-test statistic is there. Note, it doesn't tell us the sample size right here, so it is important to know how big the sample size is. And then your p-value from the t-test. And absolutely, if you have this output, you don't have to use the t-table. You can just use this. We're happy either way. Inference about predictions. So there are going to be a couple different types of prediction that we might be interested in talking about. So the first is probably more common, but predicting the average response value for all subjects that have a specific value of the explanatory variable. So maybe I want to know the average college GPA for all high school students with a 3.5 versus predicting an individual response. So saying, let's say I have a new student in my data set and they have a 3.5. What do I predict their college GPA is going to be? And things to note is that for an average of all individuals, that's not going to fluctuate as much as just one individual. The GPA of one individual can fluctuate a lot more than the average for all of them. So the predicted value, so where you're starting your point estimate, is going to be the same for both of them, but it's the margin of error. So like how wide the interval gets, that's going to be different. So if you're making a prediction for just one new individual, it's going to be a much wider interval. So your margin of error will be larger. So confidence intervals versus prediction intervals. If we want to estimate the mean response for all individuals with a specific value of the explanatory, so we're trying to figure out what mu of the y values are, we would use a confidence interval. If we want an individual response, so we want to know what an individual is likely to have, like what their college GPA is going to be, it's going to be a prediction interval. So prediction intervals are wider. They're always wider than the confidence intervals. So one thing we love to do is we love to say, oh, here are two intervals. One's the confidence interval and one's the prediction interval. Oh, darn, I forgot to label them. Which is which? You know right off the bat, the wider one is the prediction interval. Every time. The wider one will always be the prediction interval. So just keep that in mind. It's going to be wider just because from individual to individual, like individuals fluctuate a lot more than the average of everybody does. So here are and before you panic, I want to introduce, these are the equations. So for the confidence interval, so y hat, so what we predict that the response will be when you plug in x, plus or minus t star times s of y hat, and there's a whole calculation there. We also have a calculation for the prediction. We will never make you do this by hand. We do not want to make you do this by hand, but we want to show you that if you look at, so this times, the key difference here is what they're multiplied by right here, right? This times s of y hat versus this is times the square root of s squared plus s squared of y hat. This is always bigger than that. So the prediction interval will always be wider. So that's worth noting. This is not something we're ever going to give you and be like, hey, we want you to calculate this by hand. This is not going to be a thing. We just want you to know where these equations, that they come from somewhere. They're anchored somewhere. But for the most part, what we will do is we will give you a couple of intervals and say, which one is which? Okay, now do the write-up. That's what we'll do. So for example, because this GPA example, we just apparently can't get enough of it, we're going to have a 95% confidence interval from 3.27 to 3.53 with a point estimate of 3.40 for the average college GPA for all students that had a high school GPA of 3.5. So like just a real quick translation here. So we want to say, okay, well, what is the college GPA when we have a high school GPA of 3.5? So if we want to say for all high school students that had a 3.5, the average GPA in college that they're estimating is between 3.27 and 3.53 with a point M estimate of 3.4. Putting in here, so with 95% confidence, the average first year college GPA of all students at the school with a high school GPA of 3.5 is estimated to be between 3.27 and 3.53 with a point estimate of 3.4. So it's going to read very, very similar to other confidence interval write-ups. The key thing is going to be You definitely need to include the word average, but then you need to imply it's for the population. So for all students at this school with a high school GPA of 3.5. That's an important detail. If you're missing that, you don't quite have it. And then is estimated to be between the interval with a point estimate of. And if there were units, you'd include them, but with GPA, there really aren't. So now we're going to repeat, but we're going to do a prediction interval. So now we're going to repeat, but we're going to do a prediction interval. So we want to interpret the 95% prediction interval 2.98 to 3.83. So notice it's wider, right? It goes lower and it goes higher than that last interval does. With a point estimate of 3.4, the point estimate should be the same for the college GPA for one new student that had a high school GPA of 3.5. So last time we wanted to estimate the average first year college GPA for all people that had a high school GPA of 3.5. This time we just want to say, okay, well, let's estimate the college GPA for just one student. So not the average of all the students with 3.5, just one new student. So it's going to actually initially read very, very similar. So caution, with 95% confidence, and I know it's a little funky putting that since it's a prediction interval, but with 95% confidence, the first year college GPA of one new student at this school with a high school GPA of 3.5, so that's the key difference here, is estimated to be between 2.98 and 3.83 with a point estimate of 3.4. So the key difference there is going to either be of one new student with a high school GPA of 3.5 or average GPA of all students with a 3.5 high school GPA. And I really can't emphasize enough, just know that if we give you two intervals and tell you one's the confidence and one's the prediction one's always wider, the confidence one is always narrower. So we've given you enough tools that you should be able to identify which is which. So this is just an example here. This is actually the high school GPA example of confidence bands and prediction bands. So not to get too complicated. So suppose there's one student here that got a 3.2. So here, this is where their point estimate is right on the line. If we wanted to estimate for all students with the, well, actually, tell you what, I'm going to go with this student that got a 3.5. We were doing that anyway. So from here to here, this is where we predict so that's our point estimate. And here, those are going to be the ends of the confidence interval. If you went all the way out to here, but draw a straight line. That's actually our, I somehow avoided it. That's our prediction interval. So you can see the confidence interval right here versus the prediction interval. Prediction interval is a lot wider. This is just a visualization. We will not make you use it. We just wanted to show you that those confidence intervals are going to be, they're going to be a lot narrower. They're going to be a lot closer to that point estimate than the prediction intervals. And so that's going to be it for lesson 15. Definitely check out, we have a bunch of slides showing you how to, put the data in, get a scatter plot, get your least squares regression line, get all this information that you need. It can be really, really handy. definitely strongly recommend taking a look. And I look forward to chatting with y'all on the discussion boards.